Hi, and welcome to our IROS 2021 presentation on creating 3D radar velocity maps for uncertain dynamic environments. In the future, autonomous vehicles will likely be a major part of urban environments. This includes both ground and air vehicles, such as self-driving cars and autonomous drones. As autonomous vehicles become more common, this will create an increasingly complicated and challenging environment for them to safely navigate through. Autonomous vehicles will need to be able to navigate through cities while avoiding collisions with human-driven cars, self-driving cars, pedestrians, autonomous drones, etc. Safely integrating autonomous vehicles into urban environments requires accurately modeling the flow of traffic in 3D space. Providing autonomous vehicles 3D velocity maps of their environments can help enable them to avoid collisions with other vehicles. In this work, we explore the problem of creating 3D velocity maps at both the macroscopic and microscopic levels. At both levels, the velocity maps need to include an estimate of the average behavior, as well as estimates over the uncertainty of that behavior. This means creating a 3D map where, at any given point, you can obtain the mean and variance of the velocity of objects at that point. At the macroscopic level, we model the average behavior of vehicles at different locations throughout the entire environment. This requires learning a model from a large amount of data. At the microscopic level, we model the velocity of objects surrounding an ego vehicle at a current point in time from a stream of incoming measurements. This requires learning a model from small amounts of data. Velocity mapping methods have been studied in other disciplines. However, existing velocity mapping methods are deterministic and so do not provide the needed uncertainty estimates. Occupancy mapping methods are similar to velocity mapping methods. However, occupancy mapping methods alone can only be used in environments with stationary obstacles and so are insufficient for use in urban environments. Gaussian process-based methods are able to model the average velocity of vehicles and their associated variance. However, they are generally not suited for building velocity maps on the macroscopic scale because their computational complexity grows too quickly with the number of data points. Neural networks can learn velocity maps at the macroscopic scale. However, they require large amounts of data to train on and so are not suitable on the microscopic scale. The method we present, which we call Bayesian dynamic fields, satisfies all of these requirements. Our method works by learning to map position measurements to velocity measurements from data. For example, data might be gathered using radar measurements or IMU measurements. We treat this as a regression problem, where the features that we feed to our model are based off of the position measurements, and the labels are the velocity measurements. Once we have our dataset, we use a nonlinear function to map the position measurements into a high-dimensional yet interpretable feature space. This step is needed in order to model nonlinear relationships between position and velocity in our data. Next, we learn a parametric model using Bayesian linear regression to predict a distribution over velocities from our high-dimensional features. Once our model is learned, this creates a continuous function with which the mean velocity and variance can be queried at any position in 3D space on our map. Additionally, our model can be efficiently updated online as additional data measurements come in, making it amenable to changes in the environment. In order to map position measurements to high-dimensional features, we use kernel functions. A kernel is a function that outputs a similarity metric between two different inputs. For our method, we use the squared exponential kernel because of its simplicity and interpretability. Next, we then use this kernel to define m basis functions, where x is any point in 3D space, and x tilde 1 through m are fixed points in 3D space arranged in a regular grid. Although we model the 3D environment, we will explain this concept in 2 dimensions. Each basis function is defined as the kernel similarity between x and one of the points on the grid. Gamma is a hyperparameter that controls the sensitivity of the similarity. Kernels with smaller gamma values capture correlations over larger areas. Using this kernel-based method to map positions to high-dimensional features allows our model, which is learned using Bayesian linear regression, to capture nonlinear relationships between position and velocity in the data. Now that we've mapped our position measurements to high-dimensional features, we can learn a set of weights to predict values from these features. However, as mentioned earlier, we need to learn a model that not only outputs a velocity estimate, but that also outputs an estimate over the uncertainty of that velocity. This means that our model must output a distribution over possible velocity values at any given point in space. In order to do this, we maintain a vector of distributions over possible weight values, and use Bayesian linear regression to find optimal values for the weight distributions. When using Bayesian linear regression, we use a uniform prior, which assumes that our prior knowledge about an area is minimal. Because the three directional velocity components, Vx, Vy, and Vz, are independent of one another, we learn a separate set of weights for each component. Now that we have our posterior distributions over weights, we can query our model at any position in space by converting that position into a high-dimensional feature vector and computing the dot product between the feature vector and the vector of weight distributions. Thus, we have a continuous function that, at any given point in 3D space, will output a distribution over possible velocities of objects at that point in space. As mentioned earlier, gamma in our kernel equation is a hyperparameter that controls the sensitivity of the similarity metric. The larger gamma is, the more sensitive the kernel is to small differences in the inputs. The smaller gamma is, the better it is at capturing correlations over large areas. Therefore, if the nonlinear relationships between position and velocity change at different rates across the x, y, and z spatial axes, we may want to scale them differently when applying our kernel functions. In order to do this, we can use a hyperparameter matrix of gamma values, and so select different gamma values to be applied to the x, y, and z components of the position inputs when creating our high-dimensional features. We studied the overall effectiveness of Bayesian dynamic fields at learning microscopic and macroscopic velocity maps from a variety of datasets. First, we evaluated our method on two synthetic or toy datasets, which we call the chunks dataset and the blobs dataset. On the chunks dataset, we tested the effects of using dimension-adjusted kernels. This dataset has three closely spaced chunks of data points, which each have different velocity values. When we use a higher gamma value in the x-axis, we get much crisper edges in the velocities predicted by the model than when we use the same gamma value across all axes. On the blobs dataset, we can see that our method is effective at predicting both the mean and variance of velocity from a small number of data points on a microscopic scale. Note that in the areas where there is not training data, our model predicts a very high uncertainty. We also evaluated our method on three automotive radar datasets. These datasets are obtained from high-fidelity simulators or from real-world benchmark datasets. The automotive datasets are microscopic in scale because they only model the surroundings of an ego vehicle and only have a few data points per scan. As seen here on the A-Sticks automotive radar dataset, our model learns to output high-confidence predictions in the areas where data points are present, while outputting high-variance predictions in the areas where data is sparse. We also evaluated our method on two aircraft trajectory datasets. The AirSim dataset was obtained using the high-fidelity AirSim simulator and contains 60 drone trajectories in a large area. The airport dataset contains 100 real aircraft trajectories within 30 nautical miles of the JFK airport. These datasets are macroscopic in scale. As seen here on the AirSim dataset, our model is able to predict a 3D tube of velocities surrounding several ground truth trajectories of flight velocity measurements. Among other things, these tubes can be used for risk-aware control. The JFK Airport dataset contains a complex web of flight trajectories from real aircraft over a large area and contains over 1 million data points of real aircraft tracks. As visualized here, our method is able to model this complex web of trajectories with high precision. On each of these datasets, we held out 20% of the data for testing and used the remaining 80% for training. We compared the runtime and accuracy of our method against the runtimes and accuracies of several Gaussian process-based baselines: full Gaussian process, subset of data Gaussian process, and big data Gaussian process. On almost all of the datasets, our method, Bayesian dynamic fields, has the fastest training time, and achieves similar root mean squared error to the other methods. The efficiency of our method is especially pronounced on the large datasets, such as the AirSim and the airport datasets. On these datasets, Bayesian dynamic fields is at least 10 times faster than the second fastest performing method. Okay, in summary, we presented our method, Bayesian dynamic fields, to model velocity in 3D space. The model that we learn is represented as a continuous function that can be queried at arbitrary resolutions. Our method learns to not only output mean velocity predictions, but to also output variance to reflect the uncertainty of those predictions. We demonstrate on several datasets that our method achieves similar performance to Gaussian process-based methods while only requiring a fraction of the runtime. Please see our paper for more details and results, as well as our open source code. Additionally, please feel free to contact us with any questions. Thank you.